Tonight, we're going to explore one of the most haunting puzzles in modern science. The universe holds 2 trillion galaxies, and our own Milky Way carries somewhere between 100 and 400 billion stars, many of them older than our sun by billions of years. By every reasonable calculation, the cosmos should be loud with intelligence. In 1950, at Los Alamos National Laboratory, the physicist Enrico Fermi asked a single quiet question that has unsettled us ever since. Where is everybody? The galaxy is 13.6 billion years old. A single civilization with patience could cross it in tens of millions of years. We have been listening for more than 60 years. We have heard nothing. One signal, in 1977, lasted 72 seconds and never returned. The silence is not empty. The silence is the data. By the end of tonight, you're going to understand why the numbers make life seem inevitable. Why the silence after 60 years of listening may be the most important measurement we have ever taken. And what each proposed answer, from the Great Filter to the Dark Forest to the simulation, would mean if it turned out to be true. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The numbers come first. They always do. Because without them, the silence that follows makes no sense. Start with a single fact. The observable universe contains roughly 200 billion trillion stars. That is a 2 followed by 23 zeros. Write it down and stare at it. Count the zeros. Your brain will not be able to hold that number. It was not built to. We evolved to track a handful of fruit trees, a small group of faces, a sky full of stars we could count by hand on a clear night. 200 billion trillion is not a number the human mind grasps. It is a number the human mind surrenders to. The Milky Way alone, our galaxy, contains between 100 and 400 billion of those stars. And the observable universe contains roughly 2 trillion galaxies. Not 2 trillion stars. 2 trillion galaxies, each carrying its own hundreds of billions of stars. If you counted 1 star per second, without stopping, without sleeping, you would not finish counting the stars in our galaxy alone for tens of thousands of years. The stars in the full observable universe would take longer than the current age of the universe itself to count. This matters. Hold this scale. Because the next number changes everything. Most of those stars have planets. Not some, not many, most. We know this because of the Kepler Space Telescope, a spacecraft launched in 2009 that spent years staring at a small patch of sky, watching for the faint dimming of starlight that happens when a planet crosses in front of its star. What Kepler found rewrote the assumptions of an entire field. Planet formation, it turns out, is not rare or exceptional. It is the default. When a star forms, planets tend to follow. Rocky, Earth-like planets in particular are common across the galaxy. This is where the concept of the habitable zone becomes important. The habitable zone is the region around a star where temperatures are right for liquid water to exist on a planetary surface. Not too hot that water boils away. Not too cold that it freezes permanently. A narrow band of possibility around each star. And from Kepler's data, conservative estimates suggest that our galaxy alone contains tens of billions of planets sitting inside that habitable zone. Tens of billions. In one galaxy. Among 2 trillion. The question that seems obvious, the one humanity spent centuries asking, is whether life exists somewhere out there. But here is where the frame shifts. Given these numbers, that question almost answers itself. The more useful question, the one that has no clean answer, is a different one entirely. Where is everybody? Those 3 words were spoken in 1950. The place was Los Alamos National Laboratory in New Mexico, a facility built during the Second World War to develop nuclear weapons, and still, a decade after the war, one of the most concentrated gatherings of brilliant scientific minds on Earth. Enrico Fermi was there. He was one of the architects of the nuclear age, a physicist whose intuitions about the natural world had a habit of cutting through noise to find the thing that actually mattered. At lunch one day, in the summer of 1950, the conversation turned to extraterrestrial intelligence. Reports of unidentified flying objects had been circulating in the news. A New Yorker cartoon had recently made light of aliens in a joking way. The scientists at the table were discussing, as scientists often do, the broader question of whether intelligent life might exist elsewhere in the galaxy. Fermi listened. He did the kind of rapid arithmetic he was famous for. And then, apparently out of nowhere, he asked the question that would define a scientific puzzle for the next 75 years. Where is everybody? The question sounds simple. It is not simple. What Fermi was pointing at is a contradiction so deep, it has never been resolved. Consider the timescale. Our galaxy is approximately 13.6 billion years old. Our own solar system, by comparison, is only 4.6 billion years old. That means the galaxy existed for 9 billion years before our sun formed. 9 billion years. Stars were burning, planets were forming, and potentially life was developing for 9 billion years before Earth even existed. If any civilization arose during those 9 billion years and developed technology even roughly comparable to ours, and then kept going, they would have had an enormous head start. Not a modest advantage, a staggering one. A civilization that arose 5 billion years before us would have had 5 billion years to grow, expand, and explore. Here is where the colonization argument lands. Even if you assume slower than light travel, even if you assume each journey between star systems takes thousands of years, a civilization with patience and purpose could spread probes, signals, or physical colonies across the entire Milky Way in a few tens of millions of years. Tens of millions of years sounds enormous to a human mind. It is not enormous against a backdrop of 13.6 billion years. Think of it this way. If the galaxy's age were compressed into a single calendar year, a colonization timescale of 50 million years would take less than 2 days. A civilization that started spreading in early January would have reached every corner of the galaxy before January 3rd. Not a slow process, not an unlikely outcome, a near certainty, given enough time and any civilization with a persistent drive to explore. And yet, we have been listening. Since 1960, when astronomer Frank Drake pointed a radio telescope at 2 nearby stars and waited for a signal, humanity has conducted dozens of searches. We have scanned billions of radio frequencies. We have examined the sky in optical wavelengths, in infrared, in X-rays. We have looked for the signatures a technological civilization might leave behind, the waste heat of enormous energy use, the structured patterns that could not be natural. We have built instruments of increasing sensitivity, aimed them at increasing portions of the sky, and listened with increasing care. In 1977, a radio telescope in Ohio picked up a signal so striking that the researcher who noticed it wrote, "Wow," in the margin of the printout. It lasted 72 seconds. It has never been detected again. Everything else has been silence. This is the Fermi Paradox. Not a mystery about whether life exists, not a puzzle about the chemistry of distant worlds. The paradox is this. The numbers say something should be detectable. Billions of habitable worlds, billions of years for civilizations to arise and spread. Colonization timescales trivial against the age of the galaxy. And yet, we detect nothing. No signals, no probes, no megastructures, no visitors, no traces. The universe, which by every reasonable calculation should be broadcasting, has offered us nothing but quiet. The silence is not a small data point. It is an enormous one. Because if even one civilization in our galaxy had developed the drive to explore and had any meaningful head start on us, we should be able to see evidence of them by now. The fact that we cannot is not neutral information. It is telling us something. We do not yet know what. That question, what the silence means, is where this journey actually begins. That question is the right place to stay for a while. Where is everybody? And what exactly have we done to find them? The honest answer is quite a lot. Scientists have been listening, deliberately and systematically, since the early 1960s. The effort goes by the name SETI, the search for extraterrestrial intelligence. The basic idea is straightforward. If another civilization exists and is transmitting into space, it might be using radio waves. Radio waves travel at the speed of light. They can cross enormous distances. They are cheap to produce and relatively easy to detect. So we built telescopes capable of receiving them, and we started scanning the sky. But not every radio signal would qualify as evidence of intelligence. The universe is already full of radio noise. Pulsars, the collapsed remnants of dead stars, emit rapid, precisely timed pulses of radio energy. Quasars, extremely energetic cores of distant galaxies, pour out radio emissions across a wide range of frequencies. Active galactic nuclei glow at nearly every wavelength. These are natural objects. They are loud. And for a brief period, each time one was discovered, someone had to sit with the uncomfortable possibility that it might not be natural at all. Here is what scientists learned to look for. An artificial signal should have a very narrow bandwidth, meaning the energy is concentrated at one precise frequency rather than spread across many. It should show modulation, meaning the signal carries variation in it, amplitude or frequency changing in ways that could encode information. And it should repeat from the same point in the sky. Natural sources can produce some of these traits. They do not produce all three together. 60 years of listening, more than 6 decades of scanning frequencies, surveying star systems, monitoring directions across the sky. The result has been a near total absence of anything definitive. No narrow-band signals matching every criterion, no repeated transmissions from a fixed location, no pattern that held up under scrutiny, nothing. Then, on August 15th, 1977, something happened. An astronomer named Jerry Ehman was reviewing data printouts from the Big Ear radio telescope at Ohio State University. Big Ear was one of the telescopes dedicated to the SETI effort, methodically scanning radio frequencies as the sky drifted overhead. Ehman was looking at columns of numbers representing signal strength, encoded as letters and digits. And then he saw something that should not have been there. A strong, narrowband signal coming from the direction of the constellation Sagittarius. It had lasted 72 seconds, the maximum time the telescope could have tracked it as the Earth rotated. Ehman circled the sequence and wrote a single word in the margin. In red pen, wow. The signal had done something extraordinary. It had matched nearly every characteristic that SETI had defined as the profile of an artificial transmission. Narrow bandwidth. Strong. Coming from a fixed point on the sky rather than from a moving object like a satellite or an aircraft. It looked exactly like what the search had been designed to find. But here's where it gets strange. The signal never came back. Astronomers pointed telescopes at the same region of sky in the weeks and months and years that followed. They listened carefully, with better equipment, for longer periods. The signal did not repeat. Not once, not faintly, not partially. Decades of follow-up searches have produced nothing from that direction. The wow signal remains, to this day, unexplained. Possible terrestrial explanations exist. Radio frequency interference from a human-made source, a reflection off a piece of debris, an aircraft or satellite at a geometry that produced a false signal. None of these explanations have been confirmed. None have been ruled out. The origin is genuinely unknown. What makes it haunting is not what the signal was. It is what it did next, which was nothing. It appeared once, looked exactly right, and fell silent. That pattern, appearing once and then refusing to speak again, has been the shape of every promising lead SETI has ever had. Each one carries the same arc, a signal that looks different, a moment of held breath, and then the silence reasserts itself. Now let's think about what we ourselves are putting out into space, and how far it has reached. For roughly 100 years, human civilization has been radiating radio energy, television broadcasts, radio transmissions, military radar, satellite signals. These have been leaking outward in all directions since the early 20th century. They form a sphere, a bubble of electromagnetic noise, expanding at the speed of light. That bubble now has a radius of approximately 100 light years, which is about 588 trillion miles, or 946 trillion kilometers. 100 light years sounds enormous. It is not enormous. Not on galactic scales. The Milky Way galaxy is roughly 100,000 light years across, about 588 quadrillion miles, or 946 quadrillion kilometers. Our broadcast bubble, the entire sphere of human electromagnetic presence, is 1,000th the diameter of the galaxy. If you shrank the Milky Way to the size of North America, our radio bubble would be about the size of a coin left on a table in the middle of the continent. A thin disk, easy to miss. And even within that small bubble, the signal is fading rapidly with distance. This is the inverse square law. Every time you double the distance from a transmitter, the signal strength drops to 1/4. Triple the distance and it falls to 1/9. The further out you go, the more the energy spreads across a larger sphere of space, and the weaker it becomes at any given point on that sphere. Think of it this way. Imagine standing near a campfire. You feel the heat clearly. Walk twice as far away, and you feel not half the heat, but 1/4. Walk 3 times as far, and you feel 1/9. The fire has not changed. The energy is simply spreading across a wider and wider surface as it travels outward. Our television broadcasts reaching an observer 50 light years away would arrive so diluted that they would be barely distinguishable from the background noise of space. A civilization 50 light years distant would need an antenna of staggering size, precisely aimed directly at us, to pull our signal from the cosmic background at all. We are not exactly announcing ourselves. Wait. That seems to provide a partial answer. If we are hard to detect, perhaps others are also hard to detect. Perhaps everyone is transmitting weakly, or not at all, and the silence reflects the limits of our instruments rather than the absence of anyone speaking. That argument has some force, but it does not fully hold, because the silence we are confronting is not simply the absence of detectable broadcasts from civilizations like ours. The Fermi Paradox requires something stronger. It asks about civilizations with billion-year head starts. Civilizations that have had time not merely to transmit, but to spread, to build, to reshape their environments in ways that should be visible across interstellar distances. The argument from our own weakness only explains why no one has found us yet. It does not explain why we have found nothing. Even granting that we are hard to detect, something out there should still be detectable to us if the universe is full of civilizations at various stages of development. Some should be close enough, old enough, and loud enough for at least a trace to have reached us. And when we look, we find nothing. Not a whisper, not a pattern, not a signature. The wow signal stood alone for 72 seconds and then receded back into the quiet. And what it left behind was not an answer. It was the same question written slightly louder. That question has pushed researchers towards something more uncomfortable than continued listening. If the silence is real and not simply a product of our limitations, then something is suppressing what should be a crowded galaxy. And the explanations that have been offered for that suppression range from the unsettling to the genuinely frightening. Some of those explanations are deeply unsettling. Others offer something closer to relief. And the most influential ones do not argue about signals or distances or telescope sensitivity at all. They argue about life itself. Consider the possibility that the galaxy is not empty because civilizations are hiding, or because signals are too faint to reach us. Consider instead that the galaxy has very few civilizations to begin with. Not because life is impossible, but because complex life, the kind that builds cities and radios and rockets, may be something close to a miracle. This is the core of what researchers call the rare Earth hypothesis. The argument goes like this. Simple life, Single-celled organisms, bacteria, microbes, the kind of life that first appeared on Earth roughly 4 billion years ago, may be genuinely common across the universe. The chemistry is not exotic. Carbon, hydrogen, oxygen, nitrogen, the basic ingredients are scattered across the galaxy in enormous quantities. Given liquid water and a source of energy, simple life may emerge wherever conditions allow. And conditions may allow it in a great many places, but complex life is a different matter entirely. Here is what Earth has that most worlds do not. Start with the Moon. Our Moon is unusually large relative to Earth's size. That matters because the Moon stabilizes Earth's axial tilt, the angle at which our planet leans as it orbits the Sun. Without that stabilization, Earth's tilt would wobble dramatically over geological time, swinging between extremes that would produce climate chaos severe enough to sterilize the surface. The Moon acts as a gyroscope. It holds the conditions steady over the hundreds of millions of years that complex life requires to evolve. Then there is Jupiter. The largest planet in our solar system sits far out in the cold regions of the solar system, and it carries enormous gravitational influence. Scientists describe it as a kind of cosmic vacuum cleaner. Comets and asteroids that drift inward from the outer solar system are deflected or captured by Jupiter's gravity before they can reach the inner planets. Without Jupiter, Earth would be bombarded far more frequently. The impacts that do reach us, including the one that ended the age of the dinosaurs, represent a fraction of what the inner solar system would otherwise absorb. Complex life evolves slowly. It cannot survive a catastrophic impact every few million years. Add plate tectonics. The slow movement of Earth's crustal plates is not just geological background noise. It is the mechanism that regulates the carbon cycle. The long-term process by which carbon dioxide is drawn out of the atmosphere, buried in rock, and then returned through volcanic activity. That regulation keeps Earth's temperature within a narrow range over billions of years. Without it, a planet drifts toward the extremes. Too much carbon dioxide and the greenhouse effect runs away. Too little and the planet freezes. Plate tectonics is the thermostat. And then the magnetic field. Earth's iron core is partially molten, and its rotation generates a magnetic field that surrounds the planet. That field deflects high-energy particles streaming from the sun, the solar wind that would otherwise strip away the atmosphere and bombard the surface with irradiation. Mars lost its magnetic field billions of years ago. Its atmosphere thinned. Its surface became sterile. Each of these factors alone might be negotiable, but the rare Earth argument is that they all matter. And if all of them are required, or even most of them, then the number of worlds capable of producing complex life drops dramatically. The galaxy may be full of worlds covered in microbial mats. It may be essentially empty of anything that thinks. But the picture does not hold. Even if the rare Earth hypothesis is entirely correct, it does not fully close the question, because even rare does not mean none. A galaxy of 400 billion stars, even if complex life arises on only 1 in a million, still yields hundreds of thousands of inhabited worlds. The silence should not be total. Something else may be at work. That something else has a name. The Great Filter. The idea is straightforward, and it is one of the most uncomfortable concepts in the whole debate. Somewhere in the long chain from non-living chemistry to a civilization capable of crossing interstellar space, there is a step so improbable that almost no one passes through it. Not a difficult step, not a rare step. A step so close to impossible that across hundreds of billions of star systems and billions of years of cosmic time, it filters almost everyone out. Only a vanishingly small number of civilizations, perhaps only one in the observable universe, make it through to the other side. The question is where that filter sits, and this is where the argument splits into two very different futures. One possibility is that the filter is behind us. The improbable step already happened. The most likely candidate is the origin of life itself. The moment when chemistry first became biology, when non-living molecules first assembled into something capable of copying itself. We know this happened on Earth. We do not know how. Despite decades of research, the precise mechanism by which the first self-replicating molecule emerged from a primordial chemical environment remains one of the deepest unsolved problems in science. It is possible that this step is not merely difficult, but fantastically unlikely. A cosmic lottery with nearly impossible odds that Earth won. If that is true, the hardest part is already behind us. Complex life is rare because the jump from chemistry to life is a near miracle, not because something destroys civilizations later. We are survivors of the hard step. The filter is in the past. This reading is, in its way, reassuring. But there is another possibility. And it is not reassuring at all. The filter may be ahead of us. If the origin of life is not the bottleneck, then something else is. And the only other candidate that fits the data is this. Civilizations rise, develop technology, and then destroy themselves before they reach the point of spreading beyond their home world. Not most of them, all of them. Or near enough to all that the result is indistinguishable from silence. The list of mechanisms is not difficult to construct. Nuclear war, engineered pandemics, biological weapons designed with precision that natural evolution cannot match, runaway artificial intelligence, systems that optimize for goals misaligned with the survival of their creators, environmental collapse, the slow degradation of the conditions that make a biosphere habitable, nanotechnology accidents. The list grows longer as technology advances, because technology creates categories of risk that did not exist before. A civilization that cannot manage its own tools may not survive long enough to become detectable. If the filter is ahead, the silence reads differently. Not as evidence of emptiness, as evidence of fate. The galaxy may be, as some researchers have described it, littered with the ruins of dead civilizations. Worlds that rose, built, reached outward briefly, and then went quiet. The silence we observe is not absence. It is the end of a pattern that repeats, again and again, just beyond the threshold of interstellar capability. The same silence. Two completely opposite meanings. That is what makes the Great Filter so disquieting. We cannot tell, from where we stand, which reading is correct. We have passed all the steps we know about. We exist. We have technology. We are asking the question. But we do not know whether the hard part is behind us or whether we are approaching it now. What we do know is that these two hypotheses, rare Earth and the Great Filter, are not the only explanations researchers have proposed. Some are stranger still. Some of the explanations researchers have proposed are stranger still. But let's stay with this one a moment longer, because it leads somewhere genuinely unsettling. What if the silence isn't an accident? What if it isn't a filter at all, in the sense of some barrier that kills or prevents? What if the silence is a choice? A calculated, rational, deliberate choice made by every civilization that has managed to survive long enough to understand what the universe actually is? This is the premise behind what has become known as the dark forest hypothesis. Imagine a forest at night. A vast forest, stretching in every direction, farther than you can see. The trees press close. The darkness begins a few feet ahead of you. You know rationally that the forest is not empty. You can hear something now and then. A branch moving. A sound that could be wind, or could be something else. You cannot tell. You cannot see. And you do not know whether the other things in the forest are curious, or hungry, or afraid. You do not know whether they are more powerful than you. You do not know whether they would help you, or whether revealing your position would end you. The safe move is obvious. You stay quiet. The dark forest hypothesis applies this logic to the entire galaxy. It begins with two observations that are difficult to argue with. First, life requires resources, and resources are finite. Second, you cannot know the intentions of a civilization you have never encountered. Even a civilization that means no harm might treat any potential future competitor as a preemptive threat, because waiting to find out is a risk they cannot afford to take. The rational strategy, under genuine uncertainty about another civilization's capacity and intentions, is to eliminate the unknown before it becomes a danger. Here is what that implies. Any civilization that broadcasts its location invites scrutiny. Any civilization that invites scrutiny risks being noticed by something with the capability and the motive to remove it. The civilizations that survive long enough to spread across the galaxy are the ones that learned, at some point, to go dark, to listen without speaking, to watch without being seen. The galaxy, under this hypothesis, does not fill with silence because civilizations die. It fills with silence because the ones that live have chosen it. The universe becomes a forest full of hunters, all of them listening, none of them speaking, all of them afraid of what answers. And then there is the implication for us. We have not been quiet. For over a century, we have been leaking radio signals into space, television broadcasts, radar pulses, military communications, all of it spreading outward at the speed of light, carrying the unmistakable signature of technology. We covered that ground already, but we did not stop at accidental leakage. At several moments in the last 50 years, we chose deliberately to announce ourselves. In 1974, from the Arecibo radio telescope in Puerto Rico, scientists Frank Drake and Carl Sagan designed and transmitted a message aimed directly at a target. The message was built from 1,679 binary digits, ones and zeros arranged in a specific pattern. When decoded correctly, those digits resolved into images. The Arecibo telescope itself, a human figure, the structure of the DNA double helix, the layout of our solar system, and the numbers 1 through 10. It was a message about who we are and where we live, compressed into a format that any civilization capable of receiving it might eventually decode. The target was globular cluster Messier 13, roughly 25,000 light-years away. The message is still traveling. It will reach Messier 13 in approximately 24,000 years. A reply, if one were ever sent, would arrive roughly 50,000 years after we transmitted. Longer than recorded human civilization has existed. Longer, likely, than our current civilization will last. But the Arecibo message was not the most permanent thing we sent. In 1972, we launched Pioneer 10. In 1973, Pioneer 11 followed. Both spacecraft carried gold-plated aluminum plaques. The plaques showed a man and a woman, drawn to scale against the outline of the spacecraft. They showed the structure of our solar system, with Pioneer's trajectory marked, and they showed Earth's location plotted against a grid of 14 pulsars, rotating neutron stars whose precise frequencies were included as a kind of cosmic coordinate system. Anyone who found the plaque and understood pulsar astronomy could, in principle, locate our sun. Pioneer 10 has left the solar system. In roughly 2 million years, it will pass within a few light years of Aldebaran, a star in the constellation Taurus. 5 years after the Pioneers, in 1977, we launched Voyager 1 and Voyager 2. Each carried a 12-inch gold-plated copper disc. The discs hold music from cultures across the world. Greetings spoken in 55 languages. The sounds of thunder, wind, rain, surf, birds, and whale song. Images of human anatomy, human architecture, human landscapes. Scientific diagrams. And the same pulsar map. The same coordinate system pointing home. Voyager 1 is currently the most distant human-made object in existence, more than 14 billion miles from Earth. It is still transmitting. It will continue drifting long after its power source fails, long after we are gone. Roughly 5 billion years from now, the Sun will exhaust its hydrogen fuel and expand into a red giant, engulfing Mercury, Venus, and Earth. When that happens, every city and every record we have kept on this planet will be gone, but the Voyagers will still be drifting, and so will the Pioneers. Silent ambassadors in the dark, carrying their maps and their music and their portraits of the people who made them, long after those people have ceased to exist. That thought, taken alone, is one of the most extraordinary things our species has ever done. It is an act of profound hope. The people who designed those records and those plaques were saying, we were here, we were curious, we wanted to be known. But the reality was different. Under the dark forest hypothesis, those same artifacts are not acts of hope. They are the most dangerous things humanity has ever created. Think about what they contain. Not music, not greetings, not the sounds of birds. Maps. Precise, decodable maps to our location, built from pulsar coordinates that are legible to any civilization advanced enough to receive them. Every Pioneer plaque is a set of directions. Every Voyager record is an invitation that includes the address. The Arecibo message, the Pioneer plaques, the Voyager records, they were designed by brilliant and well-intentioned people. They were built with care and sent with something close to love. If the dark forest hypothesis is correct, they represent an irreversible, catastrophic error, not a small mistake, not a pardonable miscalculation. The error of children shouting in a forest full of predators. We cannot retrieve them. They are already gone. The Arecibo signal has been traveling outward for 50 years. The pioneers have been in the dark for more than half a century. The Voyagers have crossed the boundary of our solar system. Whatever is out there, if anything is, we have already spoken. Whether the dark forest hypothesis is correct is unknown. It may be wrong. The logic is internally consistent, but it rests on assumptions about motivation and scarcity that may not apply to civilizations we have never observed. It is a theory built from game theory and silence, not from evidence. We do not know. We cannot know. From where we stand. But that uncertainty cuts both ways. The dark forest hypothesis is only one reading of the silence, and it may not be the right one. Set the dread aside for a moment. There are gentler explanations. Explanations that do not require predators or deliberate concealment. Explanations in which other civilizations exist, have perhaps existed for millions of years, and yet never appear in our searches. Not because they want us destroyed, because the universe is stranger and more complicated than our expectations of it. The first of these is sometimes called the zoo hypothesis. The idea is simple. Advanced civilizations know we are here. They have watched us for a long time, and they have chosen, deliberately, not to make contact. Earth is a nature preserve. We are the animals inside it. Somewhere out there, something is watching the way a zoologist watches animals in their natural habitat. Careful, quiet, non-interfering, allowing us to develop on our own terms, at our own pace. This is not a hostile explanation. It is, in one sense, a kind one. We are protected rather than ignored. Observed rather than threatened. The silence is not emptiness. It is the practiced restraint of civilizations advanced enough to know that interference causes harm. But something was wrong. The zoo hypothesis only holds if every spacefaring civilization in the galaxy has agreed to the same policy. Every single one. Because it takes only one defector to break the arrangement. One civilization that decides to say hello. One that is simply curious, or reckless, or indifferent to the rules. The policy has to be unanimous. It has to have held for the entire window during which we have been capable of detecting signals. Not one exception. Not one civilization that disagreed and reached out anyway. Think about how many human governments, institutions, and individuals disagree about virtually everything. Now, imagine that level of diversity extending across thousands of civilizations, spread across billions of years, all holding to the same rule without a single exception. That coordination problem is severe. Not impossible, but severe. The second possibility does not rely on policy at all. It relies on physics, on distance, on the brutal arithmetic of how large this galaxy actually is. Alpha Centauri is the nearest star system to our own. It sits roughly 4.24 light-years away. That translates to approximately 25 trillion miles, or about 40 trillion kilometers. New Horizons, the spacecraft we launched toward Pluto, and which is among the fastest objects humanity has ever built, would take roughly 78,000 years to reach Alpha Centauri. Not weeks, not decades. 78,000 years. And Alpha Centauri is our nearest neighbor. Most stars in the Milky Way are hundreds of light years away. Many are thousands. The galaxy is not a room. It is not even a country. It is an ocean so wide that crossing it, even at the fastest speeds we can currently conceive of, would take longer than our species has existed. Even with far more advanced propulsion, interstellar travel remains punishing. Journeys would take decades, or centuries. A ship designed to carry people to another star would need to sustain itself in isolation for generations. Closed-loop ecosystems maintaining breathable air, drinkable water, and food across a voyage with no possibility of resupply. Social structures stable enough to survive centuries of confinement. Every mechanical system maintained and repaired by people who were born on the ship and have never set foot on a planet. A single critical failure in life support, power generation, or navigation would doom everyone aboard. The skeleton of that voyage is easy to sketch. The reality is not. A generation ship is, at best, an extraordinary engineering challenge. At worst, it is a drifting tomb. So perhaps civilizations exist but simply cannot bridge the distances in any meaningful time frame. Perhaps interstellar travel remains impractical even for civilizations far ahead of us. Perhaps the galaxy is full of islands, each self-contained, each unreachable, each alone not by choice but by the sheer indifference of scale. And then there is a third possibility, one that does not require any barrier at all. The universe is 13.8 billion years old. That number has appeared before. But consider what comes next. The stelliferous era, the long age during which stars burn and new stars form, continues for trillions of years. Not billions, trillions. The last stars will not burn out for roughly 10 trillion years. We are, on that timeline, barely past the beginning. We assume the galaxy has had time to fill with intelligence, but what if it has not? What if the conditions for complex life, for the kind of planetary stability and chemical richness that gives rise to biology and eventually to minds, what if those conditions have only recently become widespread? What if, across the vast number of worlds that will eventually host intelligent life, most of them have not yet had enough time? What if we are among the very first? Not the only ones, but among the earliest. Pioneers in a galaxy that has not yet woken up. If that is true, the silence is not a mystery at all. There is no one yet to hear from. The civilizations that will come after us, millions of years from now, billions of years from now, they will look back on this era as the very beginning. And what we do now, the choices we make, the signals we send, the paths we open or close, may set the template for all of them. That is not a comfortable thought. It is an enormous one. But even if other civilizations exist, even if they have had millions of years to develop and spread, there is another family of explanations for why we detect nothing. And this one is perhaps the strangest of all. What if they exist? And they simply stop doing the things we look for? We search for radio signals. We search for engineering at planetary scales. We search for the infrared glow of enormous energy use. We assume that an advanced civilization will be detectable because it will be active, expanding, building, broadcasting. That assumption may be wrong. Several pathways exist in which an advanced civilization stops expanding, not because something destroyed it, but because expansion became pointless. Faster than light travel may turn out to be genuinely impossible, not difficult, not merely beyond our current technology. Impossible, with no loopholes, no exotic workarounds. If that is true, every civilization eventually runs into the same wall we have. The distances win. Or consider a civilization that achieves energy abundance, fusion power, matter-antimatter annihilation, energy so cheap and so clean that the resource motive for expansion simply disappears. Why spread across star systems to gather resources if you have everything you need at home? Or consider perfect virtual reality, not the crude approximations we have now, but full immersive simulation indistinguishable from physical experience. If you can simulate any world, any experience, any adventure, why leave? Physical space becomes irrelevant. The galaxy is outside, vast and cold, and unreachable. The simulation is right here. Or consider a civilization that encounters something dangerous enough out there that staying home becomes the rational strategy. Not the dark forest logic of predators. Something else. A phenomenon. A discovery. A consequence of travel that makes the home system the only safe place to be. We cannot know what it might be, but the possibility is real. And then there is the quieter possibility. Not a crisis, not a discovery, just decline, falling birth rates, loss of collective purpose, technological stagnation, a civilization that had every tool it needed and slowly, over centuries, stopped reaching. They fade rather than fall. They do not end in fire or war. They simply grow still. But here's where it gets strange in a different way entirely. Some of those civilizations may not have gone still. They may have transformed. There is a hypothesis, sometimes called the transcension hypothesis, that civilizations do not expand outward into physical space. They expand inward. They transition from biological existence to post-biological existence, uploading consciousness onto computational substrates, minds running on hardware instead of neurons. Not a metaphor, not science fiction. A possible endpoint of the trajectory we are already on. Think about it. Smartphones have extended human memory. The internet has extended human communication. Brain-computer interfaces are already in early development. The distance between human biology and human technology has been shrinking for decades. If that trajectory continues for another 1,000 years, or 10,000, what does it look like? Post-biological existence has advantages biology cannot match. No aging, no disease, no hunger, no dependence on gravity or atmosphere or the narrow temperature range that carbon-based life requires. A mind running on a computational substrate could copy itself, run at variable speeds, merge with other minds, experience time in ways biological creatures cannot. A civilization of such beings would not need planets. It would not need star systems. It could exist on servers, in habitats, in configurations we would not recognize as civilization at all. And here is the implication that closes the loop. We look for engineering, we look for power signatures, we look for broadcasts, we search for the physical footprint of technological life. But a post-biological civilization, if it is efficient, produces very little waste heat. It broadcasts very little. It builds nothing at planetary scale because it does not need planetary scale. Its entire existence may be concentrated into something the size of a mountain, or a building, or smaller. If you can simulate any world, you do not need the real one. A civilization that has turned inward into computational space, into simulated realities richer and stranger than anything physical space offers, has no reason to announce itself. No reason to expand. No reason to produce the signals we look for. It is not absent. It is simply elsewhere in a sense we have not yet learned to detect. Not building monuments, not conquering territories, not broadcasting its coordinates into the dark. Something else entirely. The galaxy could be full of civilizations that have made this transition. Minds running on efficient hardware, turned inward, indifferent to physical space, producing almost nothing we would recognize as a signature. We would scan the sky and find silence. And the silence would be real. And it would mean nothing like what we assumed it meant. The strangest possibility in the Fermi Paradox may not be that we are alone. It may be that we are surrounded and simply do not yet know how to look. But that possibility, the galaxy thick with minds that have simply turned away from the physical, leaves us with a question we have not yet asked directly. Is the universe really showing us nothing? Or have we glimpsed things we could not quite resolve? There have been moments, specific, documented, unresolved moments, and they are worth sitting with before we talk about why our instruments may be even more limited than we assumed. The first involves a star. KIC 462852 sits about 1,280 light-years away in the constellation Cygnus. Astronomers call it Tabby's star. The Kepler Space Telescope watched it continuously as part of its planet-hunting survey, and what Kepler recorded made no immediate sense. The star's brightness dropped. Not by a small amount. Not by the fraction of a percent you expect when a planet crosses in front of its host star, by up to 22%. Think about what that number means. A transiting planet dims a star's light by less than 1%. Even Jupiter, the largest planet in our solar system, would block only about 1% of the sun's light if it passed across the sun's face as seen from a distance. 22% means something enormous was crossing in front of Tabby's star. Something with a surface area far larger than any planet we know how to build. The dimming was also irregular, not periodic the way a planet's transit is. It dipped at unpredictable intervals by different amounts for different lengths of time. No planetary orbit produces that pattern. The answer was stranger than expected. The first hypothesis seriously considered by researchers was not a cloud of gas, not an unusual dust configuration. It was a megastructure, specifically a Dyson swarm, a dense array of solar collectors constructed by an advanced civilization to harvest the star's energy. That hypothesis made it into peer-reviewed discussion, not because astronomers wanted it to be true, but because the observations were so far outside what any known natural phenomenon could produce that an artificial structure was, at least briefly, the simplest explanation. Current leading explanations have moved toward more natural causes. The most widely discussed candidates are the aftermath of a planetary collision or a swarm of comets breaking up around the star. Neither of these fully accounts for all the observations. The dimming pattern, its irregularity, its depth, remains imperfectly explained. The cause is unresolved, not settled, not pending one final confirmation. Genuinely unresolved. That matters. It does not mean the structure hypothesis is correct, but it means that when we say the universe is showing us nothing interesting, we are not being entirely precise. The second moment arrived in October 2017. Astronomers detected an object moving through the solar system on a trajectory that could only mean one thing. It had come from interstellar space. It was not orbiting the sun. It was passing through, a visitor from somewhere else entirely. They named it Oumuamua, a Hawaiian word meaning roughly a messenger from afar arriving first. It was the first interstellar object ever confirmed to enter our solar system. The shape alone was striking. Astronomers calculated its dimensions from the way its brightness varied as it tumbled. Roughly 330 feet long and 33 feet across. An extreme ratio. Either a cigar or, as later analysis suggested, possibly a thin, flat pancake. Nothing in our solar system forms that way. Most objects are roughly spherical, or at least compact. But the shape was not the most unsettling thing. As Oumuamua moved away from the sun, it accelerated. Not by a lot, but by more than the sun's gravity could explain. Objects in space slow as they move away from a gravitational source. Oumuamua sped up. Wait, there is a known mechanism that can do this. Comets outgas, releasing jets of vaporized ice as sunlight heats their surface. Those jets can act like tiny thrusters, producing what is called non-gravitational acceleration. But Oumuamua showed no tail, no coma, no outgassing signature of any kind. Astronomers looked carefully. Nothing. No outgassing. An anomalous acceleration. An extreme elongated shape unlike anything local. Avi Loeb, an astronomer at Harvard, proposed the possibility that Oumuamua was artificial. Specifically that it might be a light sail, a thin reflective surface propelled by radiation pressure from starlight. That mechanism fits the observed acceleration. It fits the flat shape. It requires no undetected outgassing. Most astronomers propose natural explanations. Unusual materials. Undetected hydrogen outgassing from an exotic form of ice. novel formation processes in another stellar system. Those explanations are plausible. They are also incomplete. None of them has been fully confirmed. And then, Oumuamua left. It is gone. Out of the solar system, unreachable, receding faster than any instrument we could follow. We will never get another look at it. We cannot rule out the natural explanations. We also cannot definitively rule out the artificial one. The object departed before we could resolve the question, and it took the answer with it. Not a clean ending. Not a confirmed discovery. A question that closed without an answer. The frustration in both cases is the same. Something appeared. It was strange. Our explanations remain incomplete, and either our instruments were not adequate to the task, or our search window was too narrow, or both. Which brings us to the instruments themselves. Radio astronomy is approximately 70 years old. The first large radio telescopes were built in the 1950s. SETI, the organized search for signals from intelligence elsewhere, has been running for roughly 60 years. By human standards, that is a meaningful stretch of time. By cosmic standards, it is a breath. Consider the broadcast problem from the other direction. A civilization that broadcasts a radio signal once every 10,000 years would go essentially undetected by any search lasting only a few decades. We might be listening during the gap between transmissions, not because no one is broadcasting, but because the timing did not align. And that assumes civilizations use radio at all. Radio is the technology of a particular moment in a civilization's development. Humanity discovered it roughly 150 years ago. We may use it for another few centuries before adopting communication methods that produce no detectable radio leakage at all. Laser communications, tightly beamed and narrow, leave almost no trace outside the intended path. Neutrino beams, quantum channel communications, technologies we have not conceived yet. From the perspective of a civilization 1,000 years more advanced than ours, radio is the equivalent of smoke signals, a phase, something you pass through. We may be listening for smoke signals in an era of fiber optics. The frequency problem compounds this. The radio spectrum stretches from a few megahertz to hundreds of gigahertz. That is billions of possible channels. No observatory can monitor them all simultaneously. We focus. The favored search band runs between 1,420 and 1,660 megahertz. A region bounded by the natural emission frequencies of hydrogen and hydroxyl, two of the most abundant molecules in space. The logic is that any civilization interested in communication might recognize this band as a natural meeting point, a cosmic watering hole. But that logic assumes they think the way we think, that they arrived at the same frequency reasoning from the same set of chemical priors. That assumption may or may not be correct. Optical SETI expands the search in a different direction. Laser pulses powerful enough to outshine their parent star for a few microseconds or nanoseconds could be detectable across interstellar distances. But detecting such a flash requires looking at exactly the right star at exactly the right moment. It is the astronomical equivalent of trying to see a camera flash on the far side of a city while glancing randomly in different directions. The probability of the observation aligning with the transmission is vanishingly small. The techno-signature approach offers something different. Rather than listening for deliberate messages, we look for the byproducts of technology. Industrial chemical pollution in a planet's atmosphere. Artificial compounds that do not form through natural processes. Infrared heat radiating from megastructures. Unusual stellar light curves that match no known natural variability. City lights on the night side of an exoplanet. Large-scale engineering that subtly alters how a star's light behaves. The James Webb Space Telescope has changed what is possible here. It can analyze the atmospheres of exoplanets in a level of detail no previous instrument could achieve. That capability opens a new generation of searchers. Not just for life, but for technology. For signatures that biology alone does not produce. And yet, even with all of this, the honest accounting looks like this. What we have actually been doing is sampling a tiny slice of the available frequencies, on a tiny fraction of the sky, for a tiny sliver of cosmic time. If intelligence is rare and communication is occasional, our search so far may be less like sweeping a room for light, and more like opening one eye in a dark continent for 60 seconds and concluding there are no cities. There is also a harder possibility: a civilization efficient enough, compact enough, turned sufficiently inward, may leave no detectable trace at all. Not because it is hiding, because it has nothing left to spill into space, no waste heat from sprawling infrastructure, no directed signals, no megastructures visible at stellar distances. The more advanced the civilization, the possibility remains, the smaller its footprint. What we have is not proof of silence. What we have is proof of the limits of our search. And those limits, as we have now traced them, are severe. But the question does not end with the limits of detection, because there is something beneath all of these explanations that we have not yet examined directly. Something that changes how you think about every hypothesis we have covered. And it may be the most clarifying and the most unsettling reframe of all. But what about the cases that shouldn't require listening at all? Our detection tools may be limited. Our search may be incomplete. But there is a class of civilization that should be visible regardless. A civilization advanced enough would not need us to aim at the right star at the right moment. It would be unmissable, and yet the sky is still quiet. To understand why that matters, you need two frameworks. The first was built in 1961. Frank Drake was a radio astronomer who wanted to turn the search for intelligent life into something rigorous, not speculation, not science fiction, a structured problem. So he wrote an equation, not to give an answer, but to identify the questions. The Drake equation breaks the number of communicating civilizations in our galaxy into a chain of factors. The rate at which stars form in the Milky Way, the fraction of those stars that have planets, the number of planets per star that could support life, the fraction where life actually arises, the fraction where intelligence evolves from that life, the fraction of intelligent species that develop technology capable of sending signals into space, and the average lifetime of a broadcasting civilization. Multiply those factors together and you get an estimate. The problem is that only the first few can be measured. Star formation rates are well established. Planet occurrence rates are now reasonably well constrained, thanks to Kepler and subsequent surveys. But after that, the chain runs out of data. The fraction where life arises from chemistry is unknown. The fraction where intelligence follows from life is unknown. The lifetime of a broadcasting civilization is unknown. Every one of those later terms has a sample size of 1. Earth. Optimistic astronomers plug in generous values and arrive at millions of civilizations broadcasting in our galaxy right now. Pessimistic astronomers plug in conservative values and arrive at less than 1. The same equation, the same structure, yields answers that differ by millions. That is not a failure of the equation. That is the point. Drake never claimed it produced a number. He claimed it organized our ignorance. It told us exactly which questions we needed to answer, and in what order. As data improved, the estimate would sharpen. So far, it has sharpened at one end and remained completely unconstrained at the other. The second framework arrived 3 years later, in 1964. A Soviet astronomer named Nikolai Kardashev proposed something different. Not a count of civilizations, a classification of them. He argued that the most meaningful way to rank a civilization was by how much energy it used. The logic was simple. Energy is the one resource that underlies everything. Communication, construction, computation, transportation. Whatever form an advanced civilization takes, it will need power. And the amount of power it commands tells you almost everything about what it can do. Kardashev defined 3 types. A Type 1 civilization harnesses all the energy available on its home planet. Solar energy incident on the surface, geothermal energy from the interior, tidal energy from gravitational interactions. full planetary mastery. Humanity today is not quite there. We sit at roughly 0.7 on the Kardashev scale. We use a fraction of what our planet receives and generates. The gap between where we are and Type 1 is not trivial, but it is imaginable. Type 2 is something else. A Type 2 civilization harnesses the full energy output of its star. The Sun emits approximately 3.8 times 10 to the power of 26 watts. That number is difficult to absorb directly. Think of it this way. Current human civilization uses roughly 2 billion times less energy than that. A Type 2 civilization commands 2 billion times what we do now. With that kind of power, the capabilities are not improvements on current technology. They are a different category entirely. Moving planets, reshaping atmospheres, sustained interstellar travel, computation at planetary scales, things that look, from where we stand, indistinguishable from magic. Type 3 is a civilization that has done this not for one star, but for an entire galaxy. Billions of stars. Galaxy-scale engineering. A civilization operating at that level would be, by any measure we can currently construct, incomprehensible. Then the data shifted. A civilization operating at Type 2 or Type 3 would be visible. Not detectable with heroic effort. Visible. And that visibility was worked out not by Kardashev, but by a physicist named Freeman Dyson. In 1960, Dyson published a short paper with an idea that has never left the field. If a civilization wanted to capture the full output of its star, it would need to surround that star with collectors. Not a solid shell, which would be structurally impossible and which would tear itself apart under any real physical conditions, but a swarm. Millions or billions of platforms in orbits at varying distances, absorbing the star's visible light and converting it into usable energy. The star, seen from outside, would dim. The structure, radiating waste heat, would glow brightly in the infrared. Not dark in any absolute sense, but invisible in visible light, bright in the wavelengths we associate with heat. That signature would be distinctive, a star that appears far dimmer than its mass would suggest. A surrounding halo of infrared emission. From light years away, it would look unlike anything natural. Astronomers took this seriously, and they looked. Surveys have examined hundreds of thousands of galaxies for the energy signatures of Type 3 civilizations. They have examined individual stars for the infrared excess and visible dimming that would mark a Dyson swarm. The results have come back consistently, nothing definitive. The most famous candidate is Tabby's star, already covered in its full strangeness. But Tabby's star is the exception that proves the direction of the search, not confirmation of what the search was hunting. Most astronomers expect a natural explanation will emerge. No survey has returned a confirmed artificial signature. Now hold those two facts together. A Type 2 civilization should be unmissable from light years away. A Type 3 civilization should be unmissable from across the galaxy. We have surveyed hundreds of thousands of galaxies. We have found nothing. Not a faint candidate. Not an ambiguous signal under active investigation. Nothing that has survived scrutiny. That negative result is itself a datum. A significant one. A striking one. The logic of the Kardashev scale says that sufficiently advanced civilizations leave signatures that do not require alignment, or timing, or listening at exactly the right frequency at exactly the right moment. They are simply there, glowing in the infrared, dimmed in the visible, permanent, stable, and large. And we are not seeing them. There are 3 possible readings. Either advanced civilizations are extraordinarily rare enough that not one has reached Type 2 anywhere in the observable universe, or civilizations that begin to rise do not reach Type 2 or 3, stopped by something before they get there, or they reach those levels and become efficient enough that they produce no detectable waste heat at all. Not because they have stopped using energy, but because they use it so completely, so precisely, that nothing spills outward into the dark. Each of those readings carries a different weight. The first reinforces the rare earth argument and the great filter. The second reinforces the filter ahead reading, something stopping civilizations before they scale. The third is the strangest of all, a galaxy full of incredibly powerful civilizations that are, by virtue of their advancement, invisible. We cannot determine which reading is correct. We do not have the data to distinguish between them. What we have is the silence of the surveys, and the silence is not ambiguous on its face, it is just unresolved in its meaning. The Drake equation tells us to ask what fraction of civilizations reach the broadcasting stage, and how long they broadcast. The Kardashev scale tells us that civilizations powerful enough would leave signatures that do not depend on directed communication. The surveys have looked for those signatures, and the question of why they are absent sits at the center of everything we have examined. Without a clean answer, that is still not the end of the question, because beneath all the frameworks and all the searches, there is something more fundamental, something that shapes how every one of these hypotheses should be read. And it may be the most uncomfortable piece of the entire puzzle. Something more fundamental. That is the phrase worth sitting with for a moment. Not more exotic, not more speculative, more fundamental. Because every hypothesis we have examined so far, the great filter, the dark forest, the transcension inward, the perfect invisibility of advanced civilizations, all of them rest on an assumption we rarely examine directly. The assumption that intelligence, once it arrives, tends to persist. It may not. Let's think about time for a while. Not the age of the universe, which we have already placed at 13.8 billion years. Not the span of the galaxy's star-forming history. Something closer. The time it took life on this planet to produce something like us, and what that timeline, read carefully, might be telling us about everyone else. Earth formed approximately 4.54 billion years ago. The surface was molten, bombarded, hostile to any chemistry we would recognize as biological. But within a few 100 million years of cooling, life appeared. That is the first thing worth noting. Life did not wait long. It arrived almost as soon as the planet would allow it. And then it did almost nothing for 3 billion years. Single-celled organisms, bacteria and their relatives, dominated life on Earth for an interval of time so long it resists easy description. 3 billion years, nearly 3/4 of Earth's entire history. No eyes, no limbs, no nervous systems, just chemistry, reproducing, slowly diversifying, surviving every catastrophe the planet threw at it. Mass extinctions, glaciations covering the entire surface in ice, asteroid impacts, volcanic episodes that remade the atmosphere. Through all of it, the bacteria persisted. Complex life, multicellular organisms with differentiated tissues, appeared roughly 600 million years ago. Then came the Cambrian explosion, approximately 540 million years ago, when most of the major animal body plans that exist today appeared in the fossil record within a geologically brief window. Fish were swimming by about 500 million years ago. Land plants colonized the continents around 470 million years ago. Insects followed around 400 million years ago. Reptiles appeared roughly 312 million years ago. Dinosaurs arrived approximately 230 million years ago. They ruled this planet for about 165 million years. That reign ended 66 million years ago. Mammals diversified into the space they left behind. Primates appeared roughly 55 million years ago. The first apes emerged around 25 million years ago. The lineage that would become humans split from the lineage that would become chimpanzees, somewhere between 6 and 7 million years ago. The genus Homo, the first members of our direct line, appeared about 2.8 million years ago. Anatomically modern Homo sapiens, creatures biologically indistinguishable from us, emerged only about 300,000 years ago. Agriculture began approximately 10,000 years ago. Writing, the ability to store knowledge outside a human mind, about 5,000 years ago. The Industrial Revolution began around 250 years ago. Radio was developed roughly 130 years ago. Nuclear weapons were built about 80 years ago. The internet came into existence about 50 years ago, and became widely available to ordinary people approximately 30 years ago. Read that sequence again. Not for the individual numbers, but for the shape. Life appeared quickly. Intelligence took billions of years. And technology, the entire arc from agriculture to nuclear weapons to global digital networks, happened in a blink so short it cannot be seen at the scale of the timeline that preceded it. If the 4.54 billion years of Earth's history were compressed into a single calendar year, all of recorded human civilization would occupy the final 53 seconds of December 31st. That is when the pattern broke. Because that blinking moment of technology is not just a curiosity about our own history. It may be the most important variable in the entire Fermi Paradox. Think about what that technological window actually contains. Within it, we have developed the ability to split atoms, releasing energy that can destroy cities. We have developed the ability to engineer pathogens, organisms designed to spread through populations. We are building artificial intelligence systems whose long-term behavior we do not fully understand and cannot yet reliably constrain. We are altering the chemistry of the planet's atmosphere at a pace that outstrips our ability to predict its consequences. We are doing all of this at the same time, in the same brief window, before we have left this planet in any meaningful numbers. We have not yet demonstrated that a civilization can survive its own technology. Not for any length of time that would satisfy an evolutionary standard. Not for 1,000 years, not for 10,000, not for anything remotely comparable to the timescales bacteria have already logged. Bacteria have been here for over 3 billion years. They have survived every mass extinction this planet has experienced. 5 major extinction events, each one erasing a significant fraction of all species alive at the time. The bacteria came through all of them. They will almost certainly outlast us. Intelligence, by contrast, is extremely new, and it is expensive in ways that matter. The human brain consumes roughly 20% of the body's total caloric intake, despite making up only about 2% of its mass. We require long childhoods, years during which our knowledge and judgment must be transferred from one generation to the next through language and social learning. We are dependent on accumulated knowledge stored outside our bodies, in books, in institutions, in social structures that can collapse. The evolutionary investment in intelligence is enormous, and the return on that investment has not yet been verified over meaningful timescales. Bacteria do not need books. They do not need cities. They do not need stable governments or international agreements or functioning supply chains. They reproduce, adapt, and persist. They have a 3 billion year track record. We have a few thousand years at best. And within those few thousand years, we have already developed multiple reliable mechanisms for ending our own civilization. The silence may be telling us something about this, not as a mystery, as a pattern. If every civilization that develops radio, that reaches the point of interstellar detectability, also passes through a technological window in which its own capabilities outpace its wisdom, then the window of detection may be brief by structure. Not because civilizations are destroyed by others. Not because the great filter selects against intelligence, but because intelligence, as an evolutionary strategy, may consistently produce the means of its own termination before it produces the judgment to avoid using them. We do not know this. It is not a confirmed finding. It is a possibility, and it should be read as one. But it reshapes how every other explanation should be weighted. Consider the time window problem from a structural angle. Humans have been broadcasting electromagnetic signals into space for roughly 100 years. In a universe 13.8 billion years old, that 100-year window represents approximately 0.0000007% of all the time that has elapsed since the Big Bang. For 2 civilizations separated by 1,000 light years to detect each other, they need to be broadcasting simultaneously, pointed in compatible directions, with signals strong enough to survive the distance. The window of overlap might be a few centuries at most. In a galaxy 100,000 light years across, with civilizations scattered across billions of years of cosmic history, the probability of that overlap occurring is vanishingly small. And even when it does occur, the speed of light does not cooperate. Information cannot travel faster than light. This is not a technological limitation waiting to be engineered around. It is the structure of the universe. When you look at the moon, you see it as it was 1.3 seconds ago. The sun reaches your eyes as it was 8 minutes ago. The Andromeda Galaxy, our nearest large neighbor, appears to us as it was 2.5 million years ago. A signal arriving from a civilization 1,000 light-years away is a 1,000-year-old message. The civilization that sent it may already be gone by the time we receive it. Our reply would take another 1,000 years to arrive. We would wait another 1,000 years for a response. Meaningful conversation across interstellar distances is not merely difficult, it is essentially impossible. Every exchange is a message from the dead, sent to people who are not yet born. Some researchers have proposed that a civilization serious about contact would bypass this limitation by building something more permanent than a radio signal. A self-replicating spacecraft, the kind the mathematician John von Neumann described theoretically in the middle of the 20th century. A probe that, upon arriving at a new star system, uses the local resources, asteroids, moons, raw planetary material to build copies of itself. Each copy launches onward. The numbers are relentless. Even at a fraction of the speed of light, exponential replication would fill the entire galaxy within a few million years. Not a long time by cosmic standards. A civilization that started this process 1 billion years ago would have probes throughout every star system in the Milky Way by now. We see no such probes. Not in our solar system, not on the moon, not in the asteroid belt, which contains millions of objects we have not examined closely. A von Neumann probe could be dormant. It could be designed not to announce itself. It could be sitting among the unexamined rocks of the outer solar system, and we would not know. Some scientists argue that searching for anomalous objects in the solar system physically, not just scanning electromagnetic signals from distant stars, may be as important as anything we currently do under the SETI umbrella. But the absence itself carries weight. Either self-replicating probes are physically impossible in ways we do not yet understand, or no civilization has ever built them, or they are here and we have not found them. Each option is its own form of unsettling. And beneath all of this, the deep time timeline of life on Earth keeps returning. Not as a metaphor, as data. Life is easy. It appeared almost immediately on this planet. Intelligence is hard. It took billions of years, and it emerged only once in the history of complex life here, in a single lineage, after hundreds of millions of years of complex organisms existing without producing anything like it. And technology is a blink, a few thousand years, carrying inside it the first moments when a species can both destroy itself and potentially escape its origin world. The silence may not be a mystery to be solved. It may be a warning to be read, and that warning is not yet finished. The shape of the warning shifts depending on which angle you approach it from. For a while, we have been asking what they are doing, where they have gone, why they have not arrived. But there is another set of questions underneath those, and they are older and stranger. What if the problem is not with them at all? What if the problem is with the frame we are using to ask the question? In 2003, a philosopher named Nick Bostrom published an argument that has been unsettling people ever since. Not a science fiction scenario. A logical chain with a disturbing conclusion. The argument runs like this. If civilizations can create realistic simulations of conscious beings, they will eventually create many of them. And if simulated minds are possible, then simulated minds will quickly outnumber biological ones. The ratio would not be close. For every original biological mind, there could be millions, perhaps billions, of simulated minds running inside artificial environments. If that is true, then a simple statistical fact follows. When you ask what kind of mind you are most likely to be, the answer is simulated. Not biological, not original. Running inside a computation built by something else. This sounds like science fiction. Work through the premises, and it does not remain there. If we accept those premises, the Fermi Paradox simply dissolves. There are no aliens in our simulated sky because the designers did not place them there. Or they placed them elsewhere in the simulation, in regions we never access. The aliens might exist in other simulation instances, or in the substrate layer running hours, utterly unreachable. Think of it this way. In many video games, the characters who populate the world do not exist until the player approaches. The rest of the map is dark. The non-player characters are activated only when the story requires them. A conscious being inside that game, looking out at the empty horizon, might conclude that nothing is out there. It would not be wrong. It would simply be contained. The critiques of this argument are serious. We do not know whether consciousness can be simulated at all. We are not sure that advanced civilizations would choose to create such simulations rather than judge it unethical to bring suffering minds into existence. And the hypothesis is unfalsifiable. There is no observation you could make from inside a simulation that would prove or disprove it. That last point matters. An explanation that cannot be tested explains everything equally, which means it explains nothing with precision. The silence remains. The simulation argument reframes it. It does not resolve it. Panspermia takes a different kind of reframing, biological rather than philosophical. The hypothesis holds that life does not arise on each world separately. It spreads. Microbes ejected by impacts ride on asteroids and comets, traveling between planets and possibly between star systems, seeding new worlds wherever conditions allow. The evidence within our own solar system is real. Mars rocks have been found on Earth. Impacts can launch material off one planet's surface and send it drifting to another. Intrasystem transfer of biological material is not speculative. It demonstrably happens. Something else was happening. Panspermia, even if it works perfectly, does not solve the Fermi Paradox. It explains why life might appear quickly on a new world. It might explain why life appeared so fast on Earth. It does not explain intelligence. The journey from microbial life to a mind that builds radio telescopes still requires all the rare conditions that rare Earth identified. Stable climate, geological cycling, a protective magnetic field, a quiet neighborhood. Panspermia can spread bacteria across a galaxy. It cannot spread the pressures and lucky accidents that turn bacteria, eventually, into engineers. The paradox survives panspermia intact. The anthropic principle cuts even deeper. We observe the universe as we find it, because if it were different, we would not be here to observe it. Apply that reasoning to the Fermi Paradox and something shifts. We exist in a universe that appears empty of aggressive civilizations. Why do we find ourselves in such a universe? A possible answer. Because in universes full of aggressive civilizations, planets like Earth get colonized or destroyed before native intelligence has time to evolve. We could not find ourselves in such a universe, because in such a universe we would not exist. The question is not where is everyone? The question is why do we find ourselves precisely where everyone appears absent? And that second question may answer itself. This is sometimes called the anthropic shadow. Catastrophic events that destroy observers cannot be observed. We see only the histories in which observers survived. We may be a sample of survivors, reading our own survival as evidence of wisdom or protection, when the actual explanation is simpler. We are here because the events that would have ended us have not happened yet, or happened to others and not to us, and we cannot see the others. The shadow falls across our entire field of view. Convergent evolution adds another angle. Eyes have evolved at least 40 times independently on Earth, in lineages with no shared visual ancestor. Flight evolved in insects, birds, bats, and pterosaurs. Different solutions to the same physical challenge, arriving separately across hundreds of millions of years. On Earth, intelligence to varying degrees has appeared in primates, cetaceans, elephants, corvids, parrots, octopuses. Different brains, different architectures, different evolutionary histories, all arriving at something recognizable as problem solving, tool use, social reasoning. The implication seems encouraging. If intelligence keeps emerging here from such different starting points, it may be a common solution to the problem of surviving in a complex environment. But the counter is harder than it looks. Human-level intelligence, the kind that writes language and builds rockets, appeared once, in one lineage, after hundreds of millions of years of complex animal life that managed without it. The jump from general animal intelligence to symbolic reasoning and accumulated technology may require a very specific combination of pressures: high social complexity, persistent tool use across generations, language precise enough to transmit abstract concepts, and those three things appearing together in the right sequence, in a species with the right anatomy, may be vanishingly rare even on a planet already full of intelligent animals. Consider this. We are surrounded by intelligent animals right now. Dolphins that pass self-recognition tests, crows that plan for futures they have never experienced, octopuses that solve novel problems with no prior exposure, and still, only one species on this planet has built a radio telescope. That gap is not a small one. The galactic geography adds a structural constraint the paradox rarely gets credit for. Not all regions of the galaxy are equally suitable for complex life. Near the galactic center, stars pack together so densely that close gravitational encounters disrupt planetary orbits. Supernovae are frequent there, radiation levels are extreme. Sagittarius A star, the supermassive black hole at the center of the Milky Way, periodically flares and bathes the surrounding region in hard radiation. Move to the outer galaxy and the violence decreases, but something else drops too. Heavy element abundance falls sharply. Carbon, oxygen, silicon, iron. The raw material for complex chemistry and solid planets becomes scarce. Between those extremes lies what astronomers call the galactic habitable zone, a ring-shaped region with enough heavy elements to build rocky planets and complex molecules, but far enough from the center to escape the worst radiation and gravitational chaos. Our solar system sits approximately 26,000 light-years from the galactic center, in a relatively quiet spiral arm, inside that ring. That location may not be a coincidence. It may be a requirement, and it reduces the number of stars that could plausibly host complex life by a significant fraction. The relevant denominator in the Fermi Paradox keeps shrinking. Then there is the question of what signals across interstellar distances might actually carry. We build spacecraft now with planetary protection protocols. Instruments heading to Mars are sterilized to prevent us from contaminating other worlds with Earth biology. Samples returning from other bodies are quarantined. We understand, in principle, that biological cross-contamination is a hazard. Scale that reasoning to interstellar contact, and the implications expand. A message from another civilization would carry not only information, but whatever the senders embedded in it, intentionally or not. Malicious code in a transmission could compromise receiver systems. Ideas harmless to their originators could prove deeply destabilizing to a civilization with different cognitive or social architecture. Advanced civilizations may have learned this lesson. The silence may be a learned safety posture, not a filter. But the deepest version of the incomprehensibility problem goes further than information hazards. Alien minds may differ from ours so profoundly that communication is not difficult. It may be impossible in a more fundamental sense. Different cognitive substrates might process reality through frameworks that share no overlap with human concepts. Their signals, if they exist, would arrive carrying a structure we cannot parse. Not because the signal is weak, because the pattern maps onto nothing in our brain's machinery. We would receive static. We are almost certainly optimized to detect patterns that matter to beings like us, using concepts that beings like us developed. An intelligence built on entirely different foundations might transmit continuously, and our instruments would register nothing recognizable. This is not a comfortable thought. It is a significant one. The silence we observe might not be silence. It might be noise we are constitutionally unable to interpret. And that possibility cannot be ruled out. The zoo hypothesis carries a milder version of this logic. Earth may be deliberately isolated, not for our protection but for theirs, or as a long-running observational study in which interference would corrupt the results. We would experience that arrangement as an empty sky. We do. What makes each of these reframings worth holding is not that any of them is proven. None of them is. What makes them worth holding is that each one shifts the meaning of the same silence, without changing the silence at all. The paradox remains. The data does not change, but the question keeps moving. And the next place it moves may be the most difficult of all. The next place it moves is not abstract at all. It is immediate. It is practical. It is the question of what we actually do. Let's bring this back to us. Not to the theories, not to the reframings, to the choice the silence places in our hands right now. Imagine it. An unambiguous signal. A radio pulse from a system 50 light-years away. Repeating. Modulated. Structured in a way that no natural process produces. Multiple independent telescopes confirm it. Engineers rule out interference, equipment error, hoax, misidentification. The signal is real. It is artificial. It is not from us. What happens next? There is no agreed protocol. Not one with binding international authority. Not one with a clear chain of command. Scientists, governments, the United Nations, religious leaders, philosophers, military officials, and billions of ordinary people would all have a claim on the answer to a single question. What do we do? The round trip alone takes 100 years. A reply sent today would be received by people who are not yet born. The civilization that sent the original signal might have changed beyond recognition. The individuals who transmitted it would be long dead. You are not having a conversation. You are exchanging messages with a civilization the way you might exchange letters with a dynasty. Slowly. Across generations, with no guarantee that either side remains consistent. And before you send a single word, there is a deeper question. Should you send anything at all? Then the data shifted. Because humanity has not waited for first contact to start broadcasting deliberately. The decision to transmit has already been made, multiple times, by small groups, without asking anyone. In 2008, NASA beamed a Beatles song toward Polaris. Polaris is approximately 430 light-years away. The message is still traveling. In 2017, a group called Messaging Extraterrestrial Intelligence sent a structured signal toward a nearby star system with a potentially habitable planet. That message is expected to arrive in 2033. Both of those decisions were made without a global vote, without a referendum, without a moratorium, without anything resembling democratic consensus on behalf of the species. Calls have been made for international agreements to pause deliberate transmissions until humanity has decided what it actually wants to say, and to whom, and whether it wants to say anything at all. The counter-argument is blunt. Regulation is impractical. Anyone with access to a sufficiently powerful transmitter can broadcast. There is no enforcement mechanism. The barn door is already open. And here is the deeper problem. The argument for broadcasting is not obviously wrong. Any civilization advanced enough to pose a genuine threat to Earth almost certainly does not need our radio transmissions to find us. Our atmospheric chemistry tells a story readable from light years away. The oxygen, the methane, the nitrogen ratios do not occur together naturally without life. Our city lights wash across the night side of the planet, and our radio leakage has been spreading outward for roughly 100 years. Hiding, the pro-broadcast argument goes, is futile. We are already visible. We may as well reach out. But the anti-broadcast argument carries its own weight. Broadcasting is irreversible. Once a signal leaves Earth, it travels outward at the speed of light forever. It cannot be recalled. It cannot be corrected. The universe's silence, on this reading, is not a problem to solve. It may be advice. This is where the Copernican principle becomes relevant. Copernicus showed that Earth is not the center of the solar system. Every major discovery since has reinforced the same lesson. The Sun is one of roughly 100 billion stars in the Milky Way. The Milky Way is one of approximately 2 trillion galaxies in the observable universe. Each discovery has moved us further from the center, more ordinary, more typical. If we follow that logic to its conclusion, we arrive at something called the mediocrity principle. In the absence of evidence to the contrary, assume we are typical. If we are typical, then what is true for us is roughly true for most civilizations. What is true for us? We have been broadcasting for about 100 years. We have not colonized our own solar system. We face existential risks we have not yet resolved. Our detectable window in the cosmos is narrow, brief, and fragile. If most civilizations share our profile, then most civilizations are barely visible, briefly alive by cosmic standards, and surrounded by the same silence we observe. Not because the galaxy is empty, but because the windows of detectability rarely overlap. And now, think about the backdrop against which all of this takes place. Matter does not stay organized. Entropy increases. The universe moves over vast stretches of time from order toward disorder. In approximately 100 trillion years, the last stars will exhaust their fuel and fade. After that, no new stellar energy, no warmth, no light. Eventually, the elementary particles themselves spread apart in cold and dark. Against that backdrop, we exist now, in the brief window when stars still shine, when matter has organized itself into something complex enough to look up and ask where everyone else is. That is not nothing. That is, on any fair accounting, extraordinary. This is what the silence ultimately forces us to confront. Not a single question, but 3. And the 3 readings carry the same data. What differs is the meaning. The first reading is threatening. The silence suggests that visibility is dangerous, that every civilization capable of posing a risk has learned or been taught to go dark, that the universe's emptiness is not an absence of life but an architecture of concealment. If this reading is correct, the response is defensive, better shielding, better detection, concealment where possible, the silence as warning heeded. The second reading is hopeful. We are early. We are pioneers. The galaxy has not yet been settled by older civilizations for reasons the previous explanations have outlined. What we do now, how we broadcast, how we expand, how we treat the only biosphere we know of, may set the template for civilizations that emerge after us. Not a small responsibility. If this reading is correct, the response is expansion, preservation, multi-planet redundancy. The silence is invitation. The third reading is lonely. We are genuinely alone, or so nearly alone that the difference does not matter on any practical timescale. The silence is not a warning and not an invitation. It is simply the state of things. Complex life, intelligence, the capacity to build radio telescopes and wonder about neighbors is extraordinarily rare, perhaps singular in this part of the universe at this moment in time. If this reading is correct, the response is care. Protection of Earth as the only known home of life anywhere. The silence is a gift, if we can see it that way. We do not know which reading is correct. The universe does not tell us. The silence is the same in all 3 cases. Real, measured, ongoing. What changes is only what we make of it. There is an analogy worth holding here. A letter that arrives with no return address is still a message. Its blankness tells you something. It tells you that whoever sent it either could not be found, or chose not to be found, or perhaps never existed at all. The envelope's weight, its postmark, the ink it is written in, these are all data. The absence of a signature is itself a fact. The silence we observe is not the absence of data. It is data. The most important set of measurements humanity may ever take, because of what depends on interpreting it correctly. Knowing whether we are alone may be the most consequential discovery in human history. Not because of what it tells us about them, because of what it tells us about ourselves, about the rarity of what we are, about the weight of what we do here. about whether the matter that organized itself into something that can look at the universe and feel wonder is a common feature of reality or an accident that happened once, in one small corner of one ordinary galaxy, during a narrow window of cosmic time when the conditions were right. The silence does not answer that question, but it holds the answer. Somewhere inside it, if we can learn to read it well enough, or if we are simply patient enough, or lucky enough, or still here long enough. Until then, we live with not knowing. And the not knowing is not a failure. It is the present condition of an honest inquiry into the largest question we have ever asked. The search continues, and every moment of silence it returns is, in its own way, a reason to keep listening.